This lesson will be on kinetic energy. Specifically, the learning objective is going to be, I can mathematically relate the velocity of an object and its kinetic energy. So being able to use kinetic energy and velocity, either to find kinetic energy, or maybe you're finding velocity from a certain amount of kinetic energy or the mass, manipulate the equation. Which, speaking of the equation for kinetic energy is kinetic energy is equal to 1/2 mv squared, where m is of course mass, and v is of course velocity. So 1/2 the mass times velocity squared. Since we have the equation for kinetic energy, we can talk about the units that kinetic energy. The units are kilogram, because of the mass, times meters per second, all of which is squared. And by all of which, I mean the meters divided by the seconds, because the velocity has meters per second, and you're squaring that. So distributing the square in, this could be also written as kilograms times meter per second squared, kilograms times meter squared divided by seconds squared. Or if you just take one factor of the meters out and have it just be multiplied at the end, you could also rewrite this as kilograms times meters divided by seconds squared, which, if you remember forces, is the definition of a Newton. Remember, because mass, and then this is the unit of acceleration. So kilogram times meters per second squared is a Newton. So that means kinetic energy also has the units of newtons per meter. This is really essential in AP physics when we talk about something called work. Here, we're going to use, for the most part, just the unit of a joule. A joule is the definition of a unit of energy. Now let's apply the kinetic energy in an example. So the example is going to be, we have a 0.5 kilogram soccer ball, and it's kicked with an initial speed of 50 meters per second. And here we just said speed because we didn't care which direction it's going. How much kinetic energy does the ball have? So kinetic energy is equal to 1/2 mv squared. So we plug in the 0.5 kilograms and then the 50 meters per second. So we square the 50 meters per second, multiply by the 0.5, multiply it by the half, and what we get is the kinetic energy is 625 joules. One thing we should notice, mass is a scalar value. It could never be negative. Negative mass does not make sense. And velocity can be negative, but when we square velocity, if it was negative, it's going to become positive. So this value for kinetic energy can't be negative. And that's fundamental because kinetic energy is a scalar value. It doesn't have a direction associated with it. And negative kinetic energy doesn't make sense, because if kinetic energy is how much energy an object has because it is moving, then the only value is, if it's moving, it's going to have some amount of kinetic energy, and if it's not moving, it's going to have 0. It doesn't make sense to have a negative kinetic energy. If it's moving in any direction, it has energy due to motion. So that's why kinetic energy makes sense to be a scalar quantity. So now we're going to compare how different variables affect kinetic energy. For example, if you have a small increase in velocity, it's actually going to result in a much larger increase in kinetic energy. And the reason for that is because velocity is being squared. So let's say you double velocity, you're actually going to quadruple. So if you 2 times the velocity, you're actually going to be 4 timesing the kinetic energy. You're quadrupling it because the double gets squared. Now, if you increase mass, you're only going to be increasing kinetic energy by the same proportion. So if you double mass, 2 times the mass, you're going to get 2 times the kinetic energy. Let's compare this to momentum. Momentum is proportional to velocity, which means if you increase velocity by, again, doubling it, you will be doubling the momentum. When you increase the velocity, you much more drastically increase the kinetic energy than the momentum. Momentum and kinetic energy have a relationship, and it is heavily used in stuff like quantum mechanics, or more advanced physics uses momentum a lot instead of velocity. We can actually write kinetic energy in terms of momentum. So what we do here is you start with a kinetic energy equation, and you multiply by mass over mass, which is just a fancy 1, so we're allowed to do that. What we get is that the kinetic energy is going to equal 1/2 the mass squared times velocity squared divided by mass. Notice here, mass squared times velocity squared. That's going to be the same thing as mass times velocity, all of which is squared, because we would It's like undistributing that square. And mass times velocity, you should recognize, is momentum. So you could write this as 1/2 the momentum squared divided by mass. So often that is written more like this. Momentum squared divided by 2m, or 2 times the mass. So you could write kinetic energy in terms of momentum. And like I said, that is heavily used in stuff like quantum mechanics.